Tonight we're going to follow a spacecraft that has already left the solar system, Voyager 2. It crossed the boundary of our solar system years ago, and right now it is still moving through the cold emptiness between the stars. It has no engine running, no destination, no way to slow down or turn back, and almost nobody ever stops to ask the most obvious question about it. Where does it actually end up? It will keep moving when the sun is gone. It will keep moving through the depths of the last stars. And it will still be moving in 10 trillion years through a universe that looks nothing like the one it left. By the end of tonight, you're going to understand what 10 trillion years actually looks like for Voyager 2, what the galaxy becomes over that time, and what it means that something we built is going to outlast everything we know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It helps this channel reach more curious minds like yours. Now let's begin. Voyager 2 was launched on the 20th of August, 1977, 16 days before its twin, Voyager 1. It left Earth on a trajectory deliberately designed to take advantage of a rare alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune were arranged in a configuration that occurs only once every 176 years. By threading a careful path through their gravitational fields, Voyager 2 could use each planet as a slingshot, picking up speed with every close approach, and ultimately reach the outer solar system without needing enormous amounts of fuel. This technique is called a gravity assist, or gravitational slingshot. The spacecraft borrows a tiny fraction of a planet's orbital momentum. The planet, being incomparably more massive, loses so little energy in return that the effect on its orbit is essentially unmeasurable. But for the spacecraft, the gain is significant. Every planetary encounter was a free boost from orbital mechanics planned years in advance and executed with extraordinary precision by teams who had never attempted anything quite like it before. The whole mission was possible because of a graduate student named Gary Flandreau, who in 1965 was working at NASA's Jet Propulsion Laboratory when he noticed that the outer planets would align in the late 1970 seconds in a way that hadn't occurred since Thomas Jefferson was president. He calculated that a spacecraft launched at exactly the right time could visit all 4 outer planets using gravity assists from each one. His insight launched a mission that would define interplanetary exploration for the next half-century. Voyager 2 swept past Jupiter in July 1979. Its instruments returned images of the Great Red Spot in unprecedented detail, a vast counterclockwise storm large enough to swallow multiple Earths. It observed active volcanic eruptions on Io, the innermost of Jupiter's 4 large moons, the first time active volcanism had ever been detected on a world other than Earth. Io is the most volcanically active place in the solar system, driven by the intense tidal heating it receives from Jupiter's gravity and the pull of the neighboring moons. The spacecraft also captured images of Europa, an ice-covered world with a subsurface ocean that planetary scientists now consider one of the most promising places in the solar system to search for microbial life. Then Voyager 2 curved around Jupiter's gravity, picked up speed, and continued outward towards Saturn, arriving in August 1981. It studied the ring system in extraordinary detail and examined the moons, including Titan, with its thick nitrogen atmosphere, the only moon in the solar system with a substantial atmosphere. Titan's surface stayed hidden beneath an opaque orange haze, its secrets not fully revealed until the Cassini-Huygens mission decades later. Saturn's gravity gave Voyager 2 the boost it needed to reach Uranus, something no spacecraft had ever attempted. It flew past in January 1986, becoming the only spacecraft in history to visit that ice giant and its system of moons and rings. Uranus is a strange world, tilted almost completely on its side. Its rotational axis is inclined about 98 degrees relative to its orbital plane, so it essentially rolls around the Sun rather than spinning upright. During Voyager 2's approach, Uranus's south pole pointed almost directly at the Sun, giving the whole planet an unusual, baffling appearance in the spacecraft's cameras. The encounter revealed 10 previously unknown moons and a ring system quite different from Saturn's. Uranus's gravity carried Voyager 2 onward to Neptune, the outermost major planet, and to this day the most distant world we've visited up close. The images were breathtaking, a vivid blue world with violent storms, including the Great Dark Spot, a storm comparable in size to Earth that had already vanished by the time the Hubble Space Telescope later looked for it. Neptune's large moon Triton orbits in the opposite direction to Neptune's own rotation, strong evidence that Triton was a captured Kuiper Belt object rather than something that formed in place. Triton's surface showed geysers of nitrogen gas erupting through its icy crust, likely driven by sunlight absorbed beneath a translucent layer of ice. Decades later, the images of Triton remain among the most alien and beautiful ever returned by a spacecraft. The Neptune encounter lasted only a few days in August 1989. Then Voyager 2 swept past, used the planet's gravity for one final push, and kept going. There was nothing left to visit. The spacecraft was already moving faster than the sun's escape velocity. It had no way to stop and no way to turn back. It was committed to the void. The spacecraft carries a suite of scientific instruments built to study planetary environments up close. Most have now been shut down, either because they've failed or because there isn't enough power left to run them. But the plasma wave subsystem still detects electric and magnetic waves in the interstellar medium. The cosmic ray subsystem still counts high-energy particles from beyond the solar system. The magnetometer still measures the local magnetic field, and the low-energy charged particle instrument remains operational. These instruments have quietly recorded the environment around the spacecraft as it drifts through interstellar space, sending that data home at the speed of light. At Voyager 2's current distance, a signal takes about 19 hours to arrive. It leaves the spacecraft, crosses more than 12 billion miles, and reaches the Deep Space Network's antennas on Earth after nearly a full day of travel. Then it's processed and folded into a body of scientific knowledge about the space between the stars that no one has ever had access to before. The region beyond the heliopause was completely unexplored until Voyager 1 crossed it in 2012. Voyager 2 followed in November 2018. The heliopause is the boundary where the solar wind, the constant outward stream of charged particles from the Sun, finally loses its battle against the pressure of the interstellar medium. Inside the heliopause, you're in the Sun's territory. The solar wind sweeps outward in all directions at hundreds of miles per second, carving out a bubble in the interstellar medium called the heliosphere. That bubble isn't a perfect sphere. The Sun's own motion through the interstellar medium compresses it on the leading side and stretches it into a long tail behind. At the heliopause itself, the outward pressure of the solar wind is exactly balanced by the inward pressure of the interstellar medium, a balance that shifts slightly as the Sun's activity rises and falls over its 11-year solar cycle. Beyond the heliopause, the Sun's wind has been stopped, and the interstellar medium takes over. You're in the space between the stars. When Voyager 2 crossed that boundary, it entered true interstellar space, and scientists immediately noticed something striking. The particle environment changed suddenly and dramatically, exactly as predicted. Inside the heliosphere, the dominant particles came from the Sun. Outside, the dominant particles are cosmic rays born in distant, violent stellar events. The spacecraft had crossed into a genuinely different physical environment, and it remains there today, moving through the interstellar medium at about 34,000 miles per hour are relative to the Sun, roughly 5 miles every second. Right now, as you're watching this, Voyager 2 is moving outward through the Milky Way. That number, 34,000 miles per hour, sounds fast until you understand the scales involved. The solar system, including the distant Oort cloud of comets at its outer edge, extends roughly 1 to 2 light years from the Sun, even at 34,000 miles per hour. It will take Voyager 2 something like 30,000 years just to clear that outer boundary in any meaningful structural sense. The nearest star to our Sun, Proxima Centauri, sits 424 light-years away. At its current speed, Voyager 2 would need roughly 76,000 years to cover that distance. But it isn't headed toward Proxima Centauri. It's moving in the direction of the constellation Telescopium in the southern sky. In about 40,000 years, it will pass within roughly 1.7 light-years of the red dwarf Ross 248. Not a dramatic close encounter, just a passing proximity in the enormous emptiness between stars. Around 296,000 years from now, it will pass within about three light years of Sirius, the brightest star in our night sky. A brilliant white star nearly twice as massive as the Sun and roughly 25 times more luminous. Even at that close approach, 3 light years is still an enormous distance, comparable to the Sun's current distance from its nearest neighbors. From Voyager 2's hypothetical vantage point during that pass, Sirius would be the brightest star in its sky, but still just a point of light, not a resolvable disk. After that passage, Voyager 2 continues on into the broader galaxy and into the deep future. No destination, no plan, just momentum. To grasp what 10 trillion years means for Voyager 2, you first need to grasp what it means for the universe. The universe is currently about 13.8 billion years old. 10 trillion years is roughly 725 times that age, a ratio that's genuinely hard to hold in your mind. Everything that has happened in cosmic history, the Big Bang, the birth of the first stars, the assembly of galaxies, the rise and fall of billions of stellar generations, the formation of Earth, the entire history of life on it, all of it fits inside less than 1% of the time span we're talking about. Over that span, the universe will pass through phases of existence most people have never considered. Phases well understood by physicists and cosmologists, but rarely discussed outside of specialist circles. Phases that will make the universe we currently inhabit look like a brief, bright, exceptional moment in an otherwise cold and quiet history. The era we live in is called the Stelliferous Era, the Age of Stars. It's the period when galaxies blaze with fusion-powered light, when new stars are continuously born from collapsing clouds of gas and dust, when the night sky from almost any vantage point is rich with starlight. This era began a few 100 million years after the Big Bang, when the first stars ignited, and it's still going today. But it won't last forever, and understanding how it ends is essential to understanding where Voyager 2 ends up. Stars run on a finite supply of hydrogen fuel, which they fuse into helium, releasing energy in the process. The relationship at the heart of it is Einstein's E-mc squared, where a small amount of mass converts into an enormous amount of energy because the speed of light is so large. In our Sun's core, roughly 600 million tons of hydrogen fuse into helium every second, and about 4 million tons of that mass is converted directly into radiated energy. That's why the Sun shines and why it can shine forever. The most massive stars, 10 or more times the mass of the Sun, burn through their hydrogen in just a few million years. They live brilliantly and die violently, exploding as supernovae and sometimes leaving behind neutron stars or black holes. Medium-sized stars like our Sun last around 10 billion years before swelling into red giants, shedding their outer layers as planetary nebulae, and leaving behind slowly cooling white dwarfs. But the smallest stars, red dwarfs, which make up somewhere around 70 to 80% of all stars in the Milky Way by number, are extraordinarily long-lived. They're small, cool, and dim, burning their hydrogen slowly at surface temperatures far lower than the Sun's, somewhere between roughly 3,100 and 6,700 degrees Fahrenheit, compared to the Sun's roughly 10,000 degrees Fahrenheit. Unlike the Sun, where convection only stirs an outer shell, red dwarfs are convective all the way through, continuously circulating their entire supply of hydrogen through the fusing core. That makes them remarkably efficient. Some red dwarfs will burn for trillions of years, and the very least massive ones, those near the theoretical minimum mass needed to sustain fusion, around 8% of the Sun's mass, have estimated main sequence lifetimes of roughly 10 trillion years. So as Voyager 2 drifts through the galaxy over the coming eons, the stellar landscape around it will change beyond recognition. The massive, brilliant blue stars that dominate our sky today will be gone within the first few 100 million years. The Sun will finish its life within the next 5 to 6 billion years. Even many red dwarfs born when the galaxy was young will have burned out within the next trillion years or so. As the eons compound toward 10 trillion years, what's left is a galaxy dominated by only the smallest, dimmest, most frugal stars, and even their numbers will be dwindling. The night sky from any hypothetical vantage point near Voyager 2 will grow darker. Not quickly, not on any human timescale, but steadily and irreversibly, over spans that make the current age of the universe look like a passing moment. Voyager 2's power source is already failing. The spacecraft runs on radioisotope thermoelectric generators, RTGs, which convert the heat of radioactive decay directly into electricity. No moving parts, no combustion, no solar panels. Just the steady, predictable decay of radioactive atoms. The fuel is plutonium-238, chosen for its half-life and the nature of its decay. It releases an alpha particle, a helium nucleus, and transforms into uranium-234, releasing heat in the process. That heat is converted to electricity through thermoelectric devices, materials that generate a voltage across a temperature difference. It's an elegant design. No fuel pumps, no combustion chambers, just physics. Plutonium-238 has a half-life of about 87.7 years. Every 87.7 years, the plutonium remaining in the generators and the power they can produce drops by half. When Voyager 2 launched in 1977, its generators produced about 470 watts, enough to run a small space heater. By 2026, that had dropped to roughly 50 watts or less, barely enough for a few incandescent light bulbs. Mission engineers have had to make increasingly hard choices about which instruments stay on. Heaters that prevent components from freezing have been switched off. Redundant backup systems have been permanently disabled. Every remaining watt has been accounted for and allocated to the highest priority science. At some point in the next several years, the power will drop too low to run any instruments, and then too low to communicate at all. The last signal will leave the spacecraft, travel for more than a day across the void, arrive at the Deep Space Network's dish antennas, and then there will be nothing more. Silence. For the first time in its existence, Voyager 2 will be completely alone. No contact with Earth, no instructions, no acknowledgement that it exists. Just the spacecraft moving through interstellar space, carrying everything placed on it in 1977. The silence won't slow it down. This is one of the most important things to understand about Voyager 2's future. In the vacuum of space, with no friction and no air resistance, the spacecraft will maintain its velocity indefinitely. Newton's first law operates perfectly out there. An object in motion stays in motion unless something acts on it. The only real force still acting on Voyager 2, aside from the negligible drag of the occasional interstellar particle, is gravity. And over the next 10 trillion years, gravity will play a profound and complicated role. As the spacecraft drifts through the interstellar medium, it will occasionally pass close enough to individual stars for their gravity to noticeably bend its path. A star 100 light-years away has a negligible effect. A star a light-year away has a small but real one. A star a tenth of a light-year away matters significantly, and a close pass within a few astronomical units of something compact and massive could be dramatic. Each close encounter nudges the spacecraft's velocity and direction, sometimes by a fraction of a degree, and over millions and billions of years, those small nudges accumulate. Voyager 2's path is not a straight line through eternity. It's a slow, wandering curve, shaped continuously by the gravitational landscape of the galaxy it moves through. A gravitational random walk, deterministic at every individual step, but after enough steps, completely unpredictable in aggregate. The single most dramatic event in Voyager 2's 10 trillion-year future is a galactic merger. The Milky Way and the Andromeda Galaxy are currently about 5 million light-years apart and closing, driven by their mutual gravity, at roughly 68 miles per second ekin. In about 4 or 5 billion years, the two galaxies will begin their first close approach. Collision is a misleading word here. When galaxies merge, individual stars almost never collide directly. The distances between stars are so vast that even as two galaxies interpenetrate, the odds of any pair of stars actually meeting are tiny. What happens instead is a gravitational restructuring. The galaxies pass through each other, their shapes wrenched by tidal forces. Long streamers of stars are pulled out into space, forming tidal tails and bridges that can stretch for hundreds of thousands of light years. Spiral arms are disrupted and flung outward. Stars on orderly circular orbits find themselves on wild elliptical paths. Gas clouds within both galaxies compress as they collide, triggering enormous bursts of new star formation, a starburst phase, in which the merging system blazes brighter than either galaxy did alone, a last magnificent flare before large-scale star formation winds down for good. The two galaxies then pull apart somewhat, swing back for a second close pass, then a third, mixing their stellar populations more thoroughly each time. Over roughly 2 to 3 billion years after first contact, they settle into a single merged structure. Simulations consistently predict the result will be an elliptical or lenticular galaxy, without the graceful spiral arms of either progenitor, a hypothetical merged galaxy sometimes nicknamed Milky Way. Voyager 2 will be along for the entire process. Its path will be reshaped by the gravitational upheaval as hundreds of billions of stars from each galaxy mix and reorganize. Stars once more than 2 million light-years away will suddenly share its gravitational neighborhood. New close encounters will occur that never would have happened had the galaxies stayed apart, but the spacecraft itself survives. It's a small metal object, and the odds it happens to sit in the direct path of another star during the chaos are vanishingly small. It emerges altered in trajectory but physically undamaged. At the center of the Milky Way sits Sagittarius A*, a supermassive black hole with a mass of about 4 million suns. Andromeda's central black hole is dramatically larger, somewhere between roughly 100 and 200 million solar masses. When the galaxies merge, these two black holes will eventually find themselves in the same system and begin drifting toward one another, though the process is extraordinarily slow. First, each sinks toward the center of the merged galaxy through dynamical friction. As a black hole moves through the surrounding stars, it gravitationally deflects them, and those stars absorb some of its kinetic energy, gradually dragging the black hole inward. Over hundreds of millions to billions of years, the two black holes approach, form a binary, and spiral closer as they radiate energy away through gravitational waves. The same kind of ripples in spacetime that LIGO has detected from merging stellar mass black holes. Eventually, in an event releasing an enormous burst of gravitational wave energy, the two supermassive black holes merge into one, sitting at the center of the newly formed Milky Way galaxy. Voyager 2, drifting somewhere in the outer reaches of that galaxy, is entirely unaffected by this in any direct sense. The gravitational waves from the merger spread outward at the speed of light, but by the time they reach the spacecraft, their amplitude is negligible. It doesn't notice. It keeps drifting, indifferent to the titanic event at the galactic core. A few billion years into Voyager 2's journey, our sun will be finished. After roughly 4–6 billion years of steady burning, it will exhaust the hydrogen in its core. Nuclear reactions won't simply stop. Instead, the core contracts and heats, a surrounding shell of hydrogen ignites, and the increased energy output causes the outer layers to swell dramatically. The sun becomes a red giant expected to expand to perhaps 100 times its current diameter. Whether it physically engulfs Earth depends on details still debated, but it hardly matters either way. Long before the sun reaches its maximum size, Earth's surface will already be uninhabitable. As the sun brightens on its approach to the red giant phase, even before the dramatic expansion begins, Earth's oceans will start to evaporate, feeding a runaway greenhouse effect that eventually boils them away entirely, pushing surface temperatures into the hundreds of degrees. Life as we know it ends. Depending on the model, this process could begin as soon as 1 to 2 billion years from now, well within the sun's ordinary main sequence lifetime. After the red giant phase, the sun will shed its outer layers in a series of pulses, creating an expanding shell of glowing ionized gas called a planetary nebula, lit from within by the exposed searingly hot stellar core. What remains at the center is a white dwarf, a dense remnant roughly the size of Earth, but containing about half the sun's original mass, composed mostly of carbon and oxygen, no longer fusing anything, just slowly radiating its stored heat into space. Over billions of years, it will cool from white to yellow to orange to red to infrared and beyond. The theoretical endpoint of that cooling is called a black dwarf, an object at essentially the temperature of the surrounding universe, cold and dark but still there. The universe isn't old enough yet for any black dwarfs to exist. Even the very first white dwarfs, remnants of the universe's earliest stars, are still comparatively warm, and won't finish cooling until long after the 10 trillion years we're contemplating here. There's something worth pausing on at this point in the story, several billion years from now. Voyager 2 was built by a civilization on a planet orbiting a star that, by then, will be cold and dark. Every engineer who built it, every scientist who planned its trajectory, everyone who has ever worked on the mission, everyone alive on Earth today, all gone for billions of years. NASA, the country that funded it, the entire structure of the civilization that made it possible, gone. The languages we think and speak in, gone or transformed beyond recognition. Everything we currently consider meaningful about human civilization in 2026 will be so ancient that no record of it may survive anywhere. And yet Voyager 2 will still be there, still moving, still carrying the sounds of a planet that no longer exists in any form we'd recognize, still carrying the golden record with its greetings in 55 languages, none of which are spoken anywhere in the universe anymore. A message in a bottle thrown into an ocean that has itself changed beyond recognition since the moment it was thrown. The spacecraft will have outlasted not just us, but the entire context in which it was created, still moving at 34,000 miles per hour on a trajectory planned in the 1970 seconds, and adjusted ever since by the gravity of every star it has passed. Going where physics sends it, without purpose in the human sense, but not without meaning. The golden record deserves extended attention, because it's the most explicitly human thing about Voyager 2. It was conceived and designed in the mid-1970s by a team that included Carl Sagan, Ann Druyan, Timothy Ferris, John Lomborg, and others, working under a mandate that was both simple and overwhelming. Put something on the spacecraft that represents Earth, in case anyone ever finds it. They had only weeks to do it. The result was a 12-inch gold-plated copper phonograph record, packaged with a cartridge, a stylus, and instructions for playing it encoded in a way that requires only a grasp of physics and mathematics. It contains 115 images encoded in analog form within the audio signal. Photographs of Earth from space, mathematical diagrams, the structure of DNA, human anatomy, people from different cultures, cities, forests, oceans. One image shows a human hand touching another hand, a simple gesture of greeting. There's a diagram of the hyperfine transition of hydrogen, the most common process in the most abundant atom in the universe, meant to provide a fundamental unit of measurement. There's a map showing the solar system's position relative to 14 pulsars. Rotating neutron stars that emit radio pulses like cosmic lighthouses, each with its own unique frequency, together forming a coordinate system that could, in principle, let anyone who recognizes the same pulsars pinpoint our location in the galaxy. The record also carries sound: thunder, wind, rain, surf on a shore, a volcano, an earthquake, birdsong, insects, the haunting songs of whales, a child's laughter, a mother's first words to her newborn, and music, a selection spanning thousands of years and dozens of traditions. The first movement of Bach's Brandenburg Concerto No. 2 in F major. Mozart's Queen of the Night aria from the Magic Flute. Music from Azerbaijan, Bulgaria, Senegal, Peru, China, India, and Japan. Stravinsky's The Rite of Spring. Louis Armstrong performing Melancholy Blues. Chuck Berry's Johnny Be Good. A Navajo night chant. An Australian Aboriginal song. The record is an attempt to say, we were here, we had music, we had language, we had cultures. We reached out because we were curious, and we wanted whoever found this to know that. It may be the most optimistic object humans have ever built. And right now it's out there, moving through the interstellar medium. In the first billion years of its journey, what does Voyager 2 actually encounter? The interstellar medium isn't empty, but it's extraordinarily sparse, roughly 1 atom per cubic centimeter on average within the Milky Way's disk, a better vacuum than anything humans can currently produce in a lab. It's composed mostly of hydrogen, with helium and trace heavier elements, some atomic, some molecular, some ionized by radiation from hot stars. It also contains microscopic dust grains, the same kind of material planets are built from, and it's threaded with cosmic rays, high-energy protons and heavier nuclei, accelerated to nearly light speed by supernova shock waves and pulsar winds, capable of penetrating materials and damaging electronics. Moving at 34,000 miles per hour, Voyager 2 sweeps through this thin stream of particles, dust, and radiation. Any single impact is trivial, but over a billion years the effects accumulate. Surfaces slowly eroding, materials slowly degrading. The RTGs will have fallen silent within the next decade or two. But the spacecraft retains thermal inertia. It won't instantly match the temperature of its surroundings, but will slowly radiate its heat away over time. In the deep cold of interstellar space, it will cool toward the temperature of the cosmic microwave background, about minus 455 degrees Fahrenheit today. At those temperatures, metals become brittle, thermal vibrations in their crystal lattices nearly cease, and the spacecraft's materials, never designed for such sustained extreme cold, begin to change in ways no lab test on Earth ever replicated. Polymers and plastics will become brittle and may crumble. Rubber will fail. Adhesives will lose their grip. What survives over a billion years and beyond is mostly the metal structure. Aluminum, titanium, steel, gold, materials that don't combust, dissolve, or evaporate at interstellar temperatures, though they do slowly accumulate radiation damage, and the occasional micrometeorite strike. Where Voyager 2 ends up at exactly 10 trillion years comes down to the mathematics of chaotic systems. Not chaos in the everyday sense, but in the technical sense used in dynamical systems theory, a system where tiny differences in starting conditions grow exponentially until wildly different outcomes. Weather is the classic example, which is why forecasts fall apart beyond a couple of weeks. Voyager 2's trajectory over 10 trillion years is chaotic in exactly this sense. Each close stellar encounter changes its velocity and direction by an amount set precisely by the geometry of that encounter, but any uncertainty in the exact positions and velocities involved, however small, compounds through every encounter that follows. A trajectory calculation off by a single meter today could diverge from the true path by light years after 10 trillion years, and we don't know the future positions of the stars involved with anywhere near the precision needed to eliminate that divergence. Even the stars themselves are subject to chaotic gravitational interactions with each other. Their positions in a million years are uncertain, in a billion years very uncertain, and in a trillion years essentially unknowable. Voyager 2's long-term path is in principle unpredictable. What we can do instead is reason statistically. The first and most confident statement we can make: Voyager 2 will almost certainly remain gravitationally bound to the galaxy. It's moving at roughly 9.5 miles per second second relative to the Sun. The escape velocity from the Milky Way in our local region is roughly 300 to 400 miles per second second. Barring an extraordinary encounter, the spacecraft simply doesn't have anywhere near the speed needed to escape. It's permanently bound to the Milky Way, and by extension to the Milkomeda system that eventually forms from its merger with Andromeda. The second statistical insight concerns how far it will spread. Traveling at 34,000 miles per hour for 10 trillion years, Voyager 2 covers a total distance on the order of 3 sextillion miles. The Milky Way is roughly 100,000 light years across, or about 600 quadrillion miles. In a straight line, that distance would let Voyager 2 cross the galaxy's full diameter around 5,000 times, but its path isn't straight. Every gravitational encounter bends it, so instead of a single long crossing, it's performing a slow, complicated random walk through the galaxy's gravitational well. Given enough time, a random walk in a bounded space eventually samples the whole accessible volume, and 10 trillion years is more than enough time for that to happen across the merged Milkomeda galaxy. Its position at any given moment, including at exactly 10 trillion years, is therefore statistically random within that volume, weighted toward the denser galactic disk, where encounters are more frequent but not confined to it. It could be deep in the core, out in the sparse halo, or somewhere in between. There's one scenario that changes everything: ejection. If, at some point over 10 trillion years, Voyager 2 happens to pass close enough to something extremely dense and massive, a neutron star or a stellar mass black hole, it could receive a gravitational kick strong enough to exceed the galaxy's escape velocity. Neutron stars pack 1 to 2 solar masses into a sphere only about 12 miles across, with gravitational fields intense enough to noticeably warp space-time. A close pass could impart a velocity of hundreds of miles per second second. and if directed favorably, that could be enough to throw the spacecraft out of the galaxy entirely. The odds of this happening are small, perhaps a few percent over the full 10 trillion years, but not zero. And if it does happen, everything downstream is different. Even if ejected, though, Voyager 2 would likely remain within the local group, the collection of galaxies, including the Milky Way and Andromeda, bound together by their mutual gravity across a few million light years. Only a truly extraordinary kick could send it beyond that boundary, and that would require an even rarer, more dramatic encounter than mere ejection from the galaxy itself. Gravitational confinement is the key idea here. Escape velocity is the minimum speed needed to break free of a gravitational field without further propulsion. On Earth's surface, that's about 7 miles per second second. Near the Sun, escaping the Milky Way requires roughly 340 to 345 miles per second second. Voyager 2 is moving at about 5 miles per second second, roughly 35 times too slow to escape on its own momentum. The galaxy holds it the way a bowl holds a dropped coin. The coin can roll anywhere inside the bowl, reach any part of its surface, but it isn't leaving. That bowl will grow as the Milky Way merges with Andromeda and eventually other local group members, but it will remain a bound structure, and Voyager 2 will remain inside it. At 10 trillion years, the universe hasn't yet reached the truly lifeless void people often picture when they imagine the far future. That comes much later. It's still barely in the tail end of the stelliferous era. The most extreme long-lived red dwarfs, those with masses around 8 to 10% of the Sun's, have theoretical main sequence lifetimes of roughly 10 trillion years, with some models pushing the most frugal survivors out to 12 or even 14 trillion. So at exactly 10 trillion years, these last stellar holdouts are still burning, just barely, emitting a deep red light far dimmer and redder than any star visible to the naked eye today, but still fusing hydrogen into helium. The galaxy at this point is dominated by stellar corpses, cooling white dwarfs, fading from white through yellow, orange, and red as they lose their stored heat, neutron stars whose pulses have long since slowed and dimmed, stellar mass black holes, invisible except through their gravity, and scattered among this graveyard of remnants, a dwindling handful of the very last living stars. Voyager 2, drifting through this landscape, passes mostly through vast dark spaces between remnants, occasionally crossing the faint light cone of a dying red dwarf. Star formation in Milky Way will have essentially stopped by this point. New stars need cold, dense gas clouds, and the merger between the Milky Way and Andromeda will have triggered one last dramatic burst of star formation as their gas clouds collided and compressed, spectacular while it lasted, but it consumed most of what cold gas remained. What's left afterward is mostly hot, ionized gas unsuited to forming new stars. By 10 trillion years, no significant star formation has occurred for billions of years. The entire stellar population consists of objects formed before and during the early post-merger period. Dark matter, meanwhile, is essentially unchanged. It doesn't decay or radiate energy away, and it barely interacts with anything except through gravity. The dark matter halos of the Milky Way and Andromeda will have merged along with everything else, still providing the overall gravitational scaffolding within which Milky Way's stars, remnants, and Voyager 2's own wandering path are all embedded. And beyond the local group, the accelerating expansion of the universe, driven by dark energy, will have carried nearly everything else out of view. Objects not gravitationally bound together get carried apart by the stretching of space-time itself. The local group, bound by its own gravity, isn't, but essentially everything beyond it will have receded beyond the cosmological horizon, its light redshifted into undetectability. From within Milky Way at 10 trillion years, the observable universe will effectively have shrunk to just the local group. The trillions of other galaxies visible in our sky tonight gone from view, not destroyed, just carried irretrievably out of reach by an expanding universe indifferent to anyone's wish to keep watching. By 10 trillion years, Voyager 2 has absorbed an almost unimaginable cumulative dose of cosmic ray bombardment, along with countless micrometeorite impacts, extreme and unrelenting cold, and the sheer passage of time. Cosmic rays are the most persistent source of damage, high-energy particles punching through the spacecraft's materials, leaving trails of ionization and displaced atoms, slowly accumulating crystal defects that make metal more brittle. 10 trillion years of that dose is roughly 10,000 times what a billion years alone would deliver, a scale of irradiation no laboratory test on Earth has ever approached. But there's no force out there trying to bend, crush, or tear the spacecraft apart. So despite all that accumulated damage, Voyager 2 is likely still there as a connected, recognizable structure. Not a cloud of debris, but a battered ancient machine. The aluminum antenna dish, still roughly 12 feet across, likely still holds its parabolic shape, pitted and darkened but intact, still pointed toward wherever Earth used to be relative to its old aim. The main spacecraft bus, aluminum and titanium, holding electronics that stopped functioning trillions of years earlier, is likely still a connected metal frame. The instrument boom, extended from the body to keep sensitive instruments away from the spacecraft's own interference, is probably still attached, its instruments dead but structurally present. The propellant tanks, empty for eons, remain as intact metal shells. The RTGs are long cold, their plutonium-238 having decayed. Through a chain of daughter products into stable lead, the golden record is likely the most durable piece of all. Gold is the most chemically inert of common metals, and in the near vacuum of interstellar space, there's almost nothing around to corrode it. No oxygen, no moisture. Its biggest threats are radiation damage and micrometeorite impacts, both of which, compounded over 10 trillion years, will have taken a real toll. The gold plating may show radiation-altered crystal structure, and the grooves encoding its information may be partially worn or filled by material kicked up during impacts. Whether that information is still recoverable is genuinely uncertain. Some of it probably is, some probably isn't. But the disk itself, the physical object, almost certainly still exists. And regardless of what remains legible, the fact of the record's creation, the decision in 1977 to put something meaningful aboard a spacecraft leaving the solar system, is permanent. It happened. That can't be undone by any amount of cosmic time. As for the atoms themselves, proton decay, if it happens at all, has never been observed, and experiments like Japan's Super Kamiokande detector have only pushed the proton's minimum possible lifetime well beyond 10 circumflex 34 years. Many models predict lifetimes even longer, around 10 circumflex 32 to 10 circumflex 38 years. At 10 trillion years, 10 circumflex 13, we're more than 20 orders of magnitude below that threshold. Every atom in Voyager 2, iron, aluminum, gold, copper, is completely stable. The spacecraft at 10 trillion years is a real, physically intact object, cold beyond anything its designers could have measured, dark in every sense, battered almost beyond recognition, but still there, still moving at the velocity physics gave it decades ago. What matters most in this thought experiment isn't really the physics, fascinating as it is. It's what the physics points toward. Voyager 2 was built by people who knew they'd never see it reach another star. They knew it would take tens of thousands of years to reach even the nearest stellar neighbor, and that they'd be long gone before that happened. They knew communication would end within decades, that power would fail within a human lifetime, and they launched it anyway, not for a measurable return on investment, but because reaching outward, extending some trace of human presence into the cosmos, was worth doing for its own sake. Humans, as far as we know, are the only species on Earth that builds things meant to outlast not just individuals, but civilizations. The pyramids were built to last. Stonehenge was built to last, but neither was built to outlast the sun. Voyager 2 won't last forever. Its structure will eventually degrade, but for longer than anything else humanity has ever made. It will remain out there, moving through the galaxy, long after everything else we've built has crumbled. The Voyager program was conceived in the 1960s. Its spacecraft, designed in the early 1970s, launched in 1977. Its planetary encounters completed between 1979 and 1989. Afterward, it became the Voyager interstellar mission, dedicated to studying the solar system's boundary and the space beyond. The team operating it has spanned generations. The original engineers and scientists are mostly gone, replaced by people who are themselves now aging, and still each day, A thin trickle of data crosses roughly 12 billion miles from a spacecraft launched when Jimmy Carter was president, and the internet didn't yet exist outside a handful of research labs. There's something quietly moving in the thought that the people who hear Voyager 2's very last signal, whoever is monitoring the Deep Space Network antennas when it arrives, will know in the moment that it's the last one. And then it will stop, and Voyager 2 will continue on without any of us, into 10 trillion years of silence. The Deep Space Network is the infrastructure that makes this communication possible. 3 large antenna complexes in California. Spain and Australia spaced roughly 120 degrees apart in longitude so that as Earth rotates, at least one complex always has a clear line of sight to any spacecraft in deep space. The largest dishes at each site are about 230 feet across, shaped to a precision of a few millimeters over their entire surface to properly focus incoming radio waves. The receivers at their focal points are extraordinarily sensitive. They have to be, because the signal from Voyager 2, after traveling 12 billion miles, arrives roughly 20 billion times fainter than the signal from a modern smartphone. It's among the faintest signals humans have ever deliberately detected, picked out only through receivers cooled to cryogenic temperatures and algorithms that average incoming noise over time to pull out a coherent signal. It works. For now. Set against 10 trillion years, the roughly 50 years of active communication with Voyager 2 amount to almost nothing. About 5 trillionths of the total span. A single heartbeat measured against a history many thousands of times longer than all of recorded human history. And yet those 50 years are the only period during which the spacecraft has any connection at all to the civilization that built it. After the final signal, Voyager 2 is entirely alone, moving through a galaxy that has no idea it exists, carrying information no one is left to receive. 10 trillion years of drifting, of simply being, of moving through a universe indifferent to its presence, with that brief 50-year parenthesis at the very beginning being the only time anyone was listening. What would it mean if someone, eventually found Voyager 2? Not in 1,000 years, not even 1,000,000, but somewhere out along that 10 trillion year journey. It's a low probability thought experiment, but worth following. Any civilization capable of finding and retrieving a spacecraft-sized object adrift in interstellar space would need instruments and patience far beyond anything we can currently imagine. The spacecraft emits no light, no radio signal after its transmitter dies, only a whisper of thermal radiation from metal sitting near absolute zero. But suppose they found it anyway. They'd have in their hands a gold-plated record, a stylus, a cartridge, and instructions for playing it, encoded in nothing but physics and mathematics. If they could decode it, they'd see photographs of Earth, of human faces, of our solar system, our DNA, our mathematics. They'd hear thunder and birdsong. They'd hear music recorded by beings who had been gone for billions, maybe trillions of years, along with the planet that made them and the star that once warmed it. The record would be the only remaining evidence that any of it had existed. A message from one species to the unknown, made by people who hoped, without ever expecting to know, that someone somewhere might someday find it. In inflation-adjusted terms, the Voyager program cost somewhere in the neighborhood of $1 billion, a large number until you weigh it against what it bought. The first detailed images of 4 outer planets, the discovery of active volcanism beyond Earth, evidence of a possible subsurface ocean on Europa, the first in situ measurements of interstellar space, and a body of data that has reshaped our understanding of the outer solar system ever since. And riding along with all of it, a golden record launched as a message from humanity itself. For roughly the cost of a fraction of a large commercial aircraft, humanity bought scientific knowledge that will inform space science for the rest of human history, and a spacecraft that will outlast human history altogether. The return isn't measurable in dollars. It's measurable in what we learned, in what it inspired, and in the strange, quiet fact that somewhere out there, right now, moving at 34,000 miles an hour through interstellar space, is a machine we built, carrying everything we chose to put on it, still going. The question we started with, where will Voyager 2 be in 10 trillion years, can't be answered with precision, but the shape of the answer is clear. Somewhere within the merged Milky Way galaxy, or possibly beyond its boundary if a rare gravitational ejection has flung it out into the wider local group, moving through a universe almost unrecognizably older than the one we know, through a galaxy populated mostly by stellar remnants, under a sky holding only the last few red dwarfs still burning amid the vast darkness between their faint deep red points of light, cold, dark, damaged, but physically present, still moving, still carrying the golden record, still carrying the sounds of thunder and birdsong and ocean surf, still carrying the music of Bach and the blues, still carrying greetings in 55 languages, still carrying a map made of pulsars, pointing back to where it came from, a location in the galaxy where, billions of years earlier, a yellow star once warmed a blue planet, and on that planet, beings arose who looked up at the sky and decided to send something out into it. The spacecraft is out there right now, moving every second, every hour, 34,000 miles an hour, in a direction set by physics and by the choices of engineers who are mostly gone. It will still be moving in a century, in 1,000 years, in 1,000,000 years, in 1,000,000,000 years, in 10 trillion years. The universe will have aged beyond recognition. The stars we know today will be memories held in no mind that still exists. The sun will be cold. Earth will be whatever it becomes after being consumed, or scorched, or simply left behind. And Voyager 2 will be out there in the dark, still going, a small metal thing with a golden disc attached. The last legacy of a species that once stood on a planet under a yellow star and reached for the sky. Good night.